Let's discuss waves and wave motion. Now, exactly what is a wave? We all know that when you're near a lake or ocean or any body of water, the smallest disturbance will cause these ripples. We recognize these as waves, but let's analyze what waves are from a physicist's perspective. A wave is quite literally a propagation of a disturbance. A rock drops in water, and the water moves because of that disturbance. The rock is what's causing the disturbance, but the water is the medium. That's very important. The medium is just the material that the wave travels through. And here's my rock propagating my disturbance. In a pond, water is the medium. The medium doesn't move with the wave. The wave literally moves through the medium. Now, in this example, we have a red triangle moving through a medium of these blue dots. As it turns out, air is a medium for our sound waves. As the waves get through the medium goes back to its original position. Whatever it was doing beforehand, it just simply gets returned. So the medium doesn't move, just the wave. Now, we're going to classify waves in a number of different ways. The first way we're going to classify waves as to whether they're mechanical or electromagnetic. A mechanical wave means that it requires a medium. Mechanical and medium. So a mechanical wave has to have something to pass through, while electromagnetic waves do not require a medium. This is light, radio, X-rays, etc. Anything that can travel in space is electromagnetic. Anything that can't travel in space, like sound, is a mechanical. There are two more ways to describe waves, and that is whether they are periodic or pulse waves. Now, a pulse wave is literally a single pulse. For example, let me bring in this diagram. Here, I'm going to give a single pulse to this bead. Now, this is a wonderful Colorado FET that helps my class understand waves quite a bit. All we're going to do is we're going to rotate this string of beads, and we're going to have a single pulse. Now, that is one event. What if instead I set up something to where I have a wave that seems to repeat itself? Let me loosen the end here and start over. Now, this is a periodic wave because it is repeating over and over. We're getting some cool effects there we'll get to in a little bit. So a pulse wave consists of a single pulse, and a periodic wave is when the source of the wave, like your hand, is going up and down. It's periodic, it's repeating. So maybe that's a good word we should write down. A periodic motion, let me get to pen, repeats. Where a pulse is 1. There's a third way to divide up waves, and that's whether they're longitudinal or transverse. Now, a longitudinal wave is a wave in which the motion of the wave is in the same direction as a given particle on that wave. So, the wave motion is this way, and the particle will move in the same direction. Oh, it'll be back and forth. Much like if you take a slinky and push it down a hallway. A transverse wave, we are moving the slinky up and down. Now, the wave still travels to the right, all right? But the particles on this wave will be going up and down. Now, since a longitudinal wave is a wave where the vibrations are parallel to the direction of the wave motion, we have sound waves are longitudinal, and they're caused by areas of compression and rarefaction. All right. A lot of times we call longitudinal waves either compression waves or pressure waves because of the areas of compression. Or sometimes we call it high pressure. And this right here would of course be low pressure or low compression. Now, it's very hard to draw a longitudinal wave with particles that are close and particles that are far. So what we tend to do is translate the center of a compression to a crest and the center of a rarefaction to a trough. When you do that, you're able to translate into a very nice sine wave. So a compression is a crest, while a rarefaction is a trough. Transverse waves, where the wave motion is perpendicular to the particle motion, has a very distinctive sine wave sort of representation. As a matter of fact, they often look like sine waves, just like our slinky wave does. The amplitude is always the distance from your equinodal line. Now, if you stretched your slinky out and it was just still, your slinky would be right along the equinodal line. When you raise it up, the slinky will follow this pattern, this sinusoidal pattern. The period is always from crest to crest. Don't try to do it along the nodal line. That gets a little confusing. Now, you remember our formulas. These are the same formulas we've used before. Frequency is going to be the number of crests divided by the total time for those crests. So if you're watching a boat and there are 15 crests in 10 seconds, your frequency would be 15 divided by 10, and our units are hertz. Period is the 1 over that. It's the total time divided by the number of cycles, and we measure period in seconds. Remember the relationship between period and frequency? Period is 1 over frequency, or you can write frequency as 1 over period. Now, remember, the source of all waves is a vibrating object. It doesn't matter if it's a slinky wave, a light wave, a sound wave. And every object that's vibrating has a certain frequency. Remember, this is our F, and we tend to describe waves with frequency. When you have, say, your hand is vibrating with a certain frequency, this frequency is passed along to the wave. Let's just review the definitions here. Frequency is the number of crests or troughs per given time, while the period is the amount of time for one complete vibration. Now, the speed of a wave depends only on the medium. Let me repeat that. The speed of a wave depends on the medium. And it is constant for a given medium. We often say the speed of light is 3 times 10 to the 8th meters per second. That is only in a particular medium. And remember, the medium is the material. The speed of a wave will change if and only if you change the medium. Now let's look at this formula right here. V is F lambda. This is a very specific formula we use when we're dealing with waves. V is going to be the speed, and remember we measure speed in meters per second. F is frequency, and it's measured in hertz. Now we're going to use this funny Greek letter lambda to denote the wavelength of our wave. So each of these waves would have a different speed. They have different frequencies, and of course, they have different wavelengths. Let's look at this problem. Suppose a jump rope is shaken to produce waves with a wavelength of 0.5 meters. So let's see, wavelength of 0.5 meters. So I know this is lambda. With the crest of a wave passing a certain point 4 times per second. What's the velocity of the wave? Alright, so this 4 hertz is my frequency. So my givens, I know lambda is 0.5 meters, and frequency is 4 hertz. The speed of the wave is what I'm looking for. That's my unknown. The equation I'm going to use, V equals F lambda. So this is 4 hertz times 0.5 meters, or 2 meters per second. And box your answer in color. What if I have a wave that has a period of 6 seconds? What's the frequency? Now, if the period is 6 seconds, you know the frequency is 1 over the period. So the frequency is 1 over 6, or 0.167 hertz. Now let's talk about the energy transferred in a wave. Waves transfer energy. They do that so well. This is one reason we use waves quite a bit. They're very efficient at transferring energy. The rate at which they transfer energy depends upon the amplitude of the wave. Let's see if this makes sense. You're in the ocean. There are some tiny waves lapping at your feet. Not a lot of energy. Well, you wait a few minutes. Suddenly a big wave comes in. You're going to feel quite a bit more energy. And it's the increased amplitude. Okay, the amplitude, you remember, is the distance from the equinoctial line to the crest. So the larger the amplitude, the more energy. For convenience sake, we're just going to comment that the energy in a wave is proportional, that's what this funky alpha means, it's proportional to the amplitude squared. So since energy is proportional to amplitude squared, we can see increasing the amplitude by a little bit will quickly increase the energy stored in a wave. Let's try a problem. If a wave's amplitude is tripled, how is the energy changed? Oh, let's see. I know the amplitude becomes 3 times the original amplitude. So we're going from a low wave to a much higher wave. We're going to pretend like this 3 times. I know that the energy is proportional to the amplitude squared. So if I put 3 in here, I see that 3 squared is 9. So the new energy will be 9 times the old energy. That's a pretty efficient way of moving energy.